Good morning, everyone. Welcome to our session, building a data-driven interior configurator using Lumen and Nanite. My name is Josh Triplett, part of Gulfstream Aerospace. Been there for a little over 16 years. I work on the advanced tech team where we, among other things, work in the Unreal Engine in the simulation areas, as well as engineering and in industrial design visualization. We do sales and design tools, which is kind of what we're going to be talking about today with our cabin creator configurator. So just to give you a brief overview of the agenda, we're going to do introductions, which we're doing now, and then I'll give it up to Brian to talk through a little bit about Gulfstream and how we use Unreal, a little bit of our history as well. We'll do a live demo of our cabin creator tool, which is what we're talking about today. And then he'll go into kind of the data conversion process that we use to bring CATIA data into Unreal. And then he's going to give it back to me to talk a little bit about the backend for our newest version 3.0 for the cabin creator tool. So what we're trying to do kind of with this session is a little bit of a shotgun effect. So we did a lot of different things to kind of bring this data-driven configurator to life in Unreal. We're going to go over some of the techniques that we used. We're going to go through some of our methodologies and thought processes behind those so that hopefully you can maybe take a few nuggets away and use them in your own projects and app development. And with that, I'll give it up to Brian.
Good morning, everyone. I'm Brian Toler with Gulfstream Customer Support. I work in systems training. I also work our advanced tech and extended realities team. I'm going to go into a little bit of the history of Gulfstream. This is our Grumman. In 1958, Grumman Aerospace gave flight to the G1. It was the first step into business aviation for Grumman and what became Gulfstream Aerospace today. There's also some fun facts. Obviously, Disney had a G1 and managed to scout out the area using his G1 for a part of that time. In 67 years, we produced over 17 aircraft. Our current fleet consists of 1 mid-cabin and 5 large cabins. In 2000, we began to develop the G650. It was our first aircraft entirely developed and certified using CAD 3D. It was also the first step towards a digital thread. This past March, we certified our G700, our largest aircraft with 5 living areas. It can seat 19 passengers, sleep 13, and has an enormous selection of interiors available. This is a photo, and this is Unreal. As you can see, we have a lot of different layout options. Each product varies and is unique to itself. So how do we make the process easier? In 2021, we started looking at building a new app that would support our sales design team. It would allow our customers to block out the aircraft and visualize material options quicker. We introduced Cabin Creator in 2022, built using Unreal Engine 4.27. Cabin Creator 2 came with some caveats, requiring hours of baking, limited layouts, usually 3 to 4 layouts per product, and limited material styles. The 3D pipeline was a much longer process too, and it could take weeks to prepare assets. Then in 2024, we migrated to Unreal Engine 5, and in a year, we were able to completely rebuild Cabin Creator from the ground up, deployed with 8 aircraft and with an unlimited amount of layouts and material combinations. Like most projects, it takes a village. The core team of Cabin Creator was 2 to 4 people at any time, and we worked with our Viz team to develop and deliver the final materials. So I'm going to jump into a demo so you guys can actually see it. I will say this is still in work, so there might be some bugs. And actually, you're seeing it before some of the customers are seeing it. So this is our G600 aircraft. We're starting in the galley, and I can move through the cabin. This is all in real time, obviously. We're using Nanite and Lumen. One of the nice features is we have a layout function, so we can come in and also change the different styles and settings on the fly. I can go into our interior section. We can go into the veneers. We can quickly change different veneer settings. I can go into the flooring We can change out our flooring, our carpet. And then we can even break out, let me go back to the seats, go into our materials, and then I'm going to break this out into a monument section. So if we want to do our seats, we have a whole section dedicated to just the seats. So we can go in and modify the colors, go into our inserts, and let's see. And quickly see our seats. So now I'm going to jump into our current pipeline. With the original Cabin Creator, it would take weeks to prepare models, UV, bring into Unreal Engine and bake scenes. Granted, we haven't defined a one-button solution, but we have managed to get the process down from weeks to hours, and in some case, minutes. Sometimes it takes even longer to actually find the assemblies than it does to actually process them. We tessellate and convert the NURBS data. This leaves us with roughly so this assembly leaves us with roughly 1.3 million for the assembly. Just for reference, the aircraft has 907 unique parts inside of it, with a 38,000 total parts. So estimated just the cabin is 702 million triangles. We apply a baseline texture to identify improper UV directions and remove additional model data. We also keep a fair amount of the internal geometry in the event that we want to open up doors, add lighting, or do other animations to it. This also leaves us with roughly, after we're done with this process, about 147,000 triangles. We could probably remove more, but it's not necessary for our application. We resize the UV across the assembly and export. We would bring the model into a digital content creator, but now with the UV editor inside of Unreal, we really can eliminate that step. The final assembly installed running in Cabin Creator is right here, and kind of like what I've shown you previously. The total time from CAD to in-engine is less than an hour. So it's been an amazing change for us with Nanite, Lumen, and all these features that Unreal has today. And with that, I'll pass it back to Josh.
All right, thanks, Brian. We've hit it at the same time there. So let's talk a little bit about the new backend. So Cabin Creator 3.0, we decided to revamp the backend a little bit. And so I'm going to kind of go through some of the processes that we use to create this data-driven backend. I have a few kind of simple examples as well that hopefully you can take back and maybe use for your projects. And to talk about Cabin Creator 3.0, I'm going to first talk about Cabin Creator 2.0 and why we kind of decided to change some things. So first off, there was basically one blueprint. This thing was enormous. It was a widget that contained all the widgets and all the blueprint. And you can see there, it was not easy to navigate around in. So what does that mean? It's really, really hard to make changes in the blueprint. Even finding things, even though it's fairly labeled, not easy to do. It was actually getting to the point where we were seeing like performance issues while navigating in the blueprint. So we were getting like 1 to 2 frames per second frame rate just navigating in the blueprint. So it was almost impossible at that point to even continue. So there was not really functions. There's a caveat. There was a few functions, but most of it was just this button, the next button, the next button, changing some variables, that kind of thing. So. Lots of duplicated functionality. If you had to change something, you had to change it on every single one of the things instead of in just a function. So here's our user interface for 2.0. Again, it was pretty much one widget, virtually impossible to find anything in it. We didn't necessarily have super standardized naming conventions even, so doing searches in that blueprint didn't work so well all the time. Sometimes you could find something, sometimes you wouldn't. Everything was hard-coded. There was no instantiation or anything like that. It was not responsive, so it would work on certain screens, not on others, which for our purposes wasn't necessarily that big of a deal because we control a lot of the hardware that it goes on, but still, we wanted to be able to build it responsive. And as you can imagine, one small change cascades. So if you have to remove a button, you have to then shift all the buttons over I mean, it's a whole process. And here's the worst part. Every single aircraft had its own application. There were 8 aircraft. If we made one change, we had to do it 8 times. So what was our solution? We were going to build it from the ground up. And this, I put this in here because this is an image of what I imagine my boss looked like when I told him we were going to completely redo this application. I don't think he was happy with that, but all right, the dream. So Cabin Creator 3.0, what were we wanting from this? First off, we wanted it to be data-driven as per this talk here. What does that mean? We wanted data files to drive the 3D functions in the UI. So rather than having everything be hard-coded, we wanted everything to come from these data files. So one of the other things we wanted from this is to be able to manipulate the data outside of the application. So rather than having to repackage every time we made a minor change, we want to be able to manipulate some of that without repackaging, as that says. And then we also wanted to make it more modular. So rather than having one blueprint, we wanted to separate everything into kind of its own constituent parts. All right, so scalable UI. We also wanted this to be scalable, so we wanted to be able to add or remove buttons without that cascading down and affecting everything else. We did not want this to be hard-coded. We wanted to use as much data-driven workflow as possible for it. We wanted it to be responsive, so we wanted it to work on a lot of the different screens. We do have everything from a laptop up to a power wall, so we wanted it to work on all these different kinds of devices. And then we wanted to use Unreal 5. So moving from Unreal 4 to Unreal 5 gave us the ability to utilize Lumen and Nanite, which is going to greatly increase our abilities to not obviously have to light map bake. With those applications, we actually, because we had to separate them out, each application was around 20 gigabytes each. So with all the textures we're putting in there, all the data, everything, you're talking about 8 times 20 gigabytes. So we wanted to do it all in one application instead, and we wanted that one application to be less than 20 gigabytes. And just to let you know, we have all of our aircraft in this application, and it's actually under 10 gigabytes now. So it's quite an impressive improvement. And then also we wanted to be able to add our layout and styling. As Brian mentioned, we're pretty limited with how just being able to do floor plans and basic seat styles, but we wanted to put all of our layout and styling in there, which there's a lot of layout and styling, and then eventually to be able to add the exterior as well. So step 1, we decided because this was going to be such a massive project, we wanted to really structure it up front. We built a wireframe diagram. This is our wireframe diagram. You're not meant to read all of this, obviously. It's way too tiny. But it's more just to show you generally kind of what it looks like. And so why do we build a wireframe? Number 1, because we wanted to be able to structure this whole project before building it. And to understand the workload. So, if you go into a project and you don't develop a wireframe first, a lot of times you have absolutely no idea how much work you're going to need to do. You don't know how much time to put into it. You can also understand the cost a little bit better. So depending on if you're bringing in third-party developers or things like that, it'll help you understand how much your cost may be up front. We also utilize this so that we could figure out which external teams within Gulfstream we were going to need. So for instance, we store some of these projects on servers, so we knew we needed to talk to infrastructure. Security is a big deal with Gulfstream, so we knew we would probably need to talk to security and bring those teams in as well. And then obviously no spaghetti code whatsoever if you do this. So data-driven, why did we want this to be data-driven? Just to kind of re-say all this, we wanted to be able to change the data without repackaging. We wanted it to be fairly easy to make minor changes. This was a big one. We wanted to be able to hook data into other apps. So if everything's stored internally in Unreal, it's a lot harder to kind of grab that data and use it within other applications. So we're kind of trying to develop a whole architecture here where we are able to use that data and the save files and things like that to hook into other applications eventually as well. Wanted the UI to be scalable and the scene also to be responsive and scalable. So we looked at a couple of different data types when we were building this application. So the first one was the CSV files. It was a pretty easy beginning one just to start with and think through. There's several pros to CSV files. Obviously, it's very widely supported. You can manipulate it in Excel, so it brings it right into data tables in Excel. It's very human readable. It's literally just strings separated by commas, so you can read it very easily. But there's also several cons to CSV files. They're one-dimensional, so it's hard to get hierarchy or objects within objects within objects. And then you're limited to only numbers and strings for a variable. We also looked at structs within Unreal itself, so there's some obvious pros with that. You can use any variable type that Unreal has. That's a nice bonus. Also human readable, you can just go into the struct and see what you have in there. However, the cons are, again, that it's one-dimensional. While you could have structs within structs, that's not always a very good idea. You can break your program pretty easily if you make changes. And you can only update and change this or really read it very easily within Unreal. And then finally, JSON, which is what we went with. So why do we choose JSON? Here's some of the pros here. It's multidimensional, so because of the use of objects, you can have objects within objects within objects. You can have lots of layers. It's widely supported, so just about everybody supports JSON. Human readable, so even though there's a few tags for coding and stuff like that, you can still go into the file and read it very easily. It's very simple, very easy to use. Here's a big one for us. As I mentioned, security is a big deal at Gulfstream. Bringing in new, even just data types sometimes can be difficult. So we are using it in a lot of applications at Gulfstream, so there's no worries about that. And it's already tied into other Gulfstream systems as well. Again, there's still cons though with JSONs. It can be difficult to manage larger JSON files because of the extra coding. That could probably be said of any data type, however. And then you are still limited with variable types to strings, bools, and numbers. So we decided to kind of break up our data files into two different types. So we've got manifests, and then we've got schemes. And I'll kind of tell you a little bit about what the difference is. So manifests are not going to change at runtime. There's a limited number, so we sort of pre-program these manifests ahead of time, and anytime we make changes, then we'll push a new manifest file. This is what's going to drive kind of what shows up in general in the app, so any of the menu options, buttons, things like that, and also what shows up in the actual scene itself. Schemes, on the other hand, do change at runtime. There theoretically could be an infinite number of them because the customers actually can make or delete different scheme files. They drive the currently selected options, and basically it's a save file. This is kind of a real high-level structure of how we're utilizing that in our system. So we're using the VA REST plugin, which is, I believe, free on the Fab Store. It's actually a REST API, so it does HTTP interactions, but it also has a pretty robust JSON management system. So we're just mostly utilizing it for that. For the time being. Down on the left here, you can see that we load the JSON manifest in. There's kind of a general, basic idea of what that might look like. We use that to then spawn the UI, and then we use it to spawn the scene itself. And then on the right there, we will load the JSON scheme. So there's kind of a general default save file for each individual option that we'll load. And again, looks pretty similar to the other one. From there, we will make changes to the scene, or the customer will make changes to the scene, and then it will save back out that JSON file. So we utilize the asset registry quite a bit in this program, in this application. So I'm going to go into this a little bit, and we'll have a quick example of what you could maybe use that for. The asset registry you can utilize to basically pull an asset based on the name and location. So anything that's in your content browser, even if it's not loaded in the scene, you can just pull that right out. You don't have to use variables or anything like that for it. So we define the name of the asset within the JSON file. So that's how we use the data file itself to drive what we pull and bring into the app. And it basically just locates the files. One thing to mention on this is that project structure is really important. So because you're going to be stringing together locations of assets, you want to have a good structure for where things are located in folders. You don't want to just have everything kind of haphazardly throughout your project. That's going to make it a lot more difficult to do this kind of data-driven workflow. And on that sense, we use a project locations manifest. So we actually have a manifest we bring in that strings together locations for folders. And the reason we do that is because if we determine at some point that we want to change where the folder is, we don't then have to change every single asset in the application. We can just change that kind of general folder structure, and it'll update automatically. Now, something else to mention is one of the things that we wanted to do was we wanted to be able to pull in UAsset files into the project post package. So you can actually, depending on how you set up your project, you can bring on UAsset projects and then use the asset registry to pull those assets that weren't cooked initially. But you have to, for the asset registry, you then have to actually update that asset registry on start. That's really expensive, so you kind of have to build a structure around how that's going to work so you're not just searching every single folder. We haven't had the time to do that yet, but that's kind of one of the things we'd like to do. All right, so here's just a really basic example of how you might use this. So up here you've got just a really, really simple JSON file. It's got a single string material called m_test_01. And then we've got a function here where we're going through two sets of sequences. Here's where we're using the VA REST subsystem. From there, we can just load a JSON from file, which we're feeding this in, this materials.json file, which is this here. You can make that relative to the content directory, which it's just right in the content directory in this sense. And then from there, we're going to get a string field called material, which is this string field here. And here's how we're actually going to build the location so that the asset registry understands it. So /game is actually your base content directory. So when you're running in game, that's what it expects rather than content. And then assets is an additional folder within that content directory. Now from there, to actually name the asset itself, we have to use the name, which here we're pulling this string. So we have m_test01. And then it expects a dot, and then that name again. So just porting in the name itself isn't enough. It needs the name dot the name again. So we're just storing that in a local variable here. And then next, we're getting our asset registry, and we're porting in that local variable we just created. We're getting the asset by the object path, which returns this data struct for the asset itself. There's a function within Unreal to get the asset itself. So this is going to give us, I believe, an object. It's going to return an object, and then we can cast to that object to whatever it is. So in this case, it's a material, so we're casting to that material and outputting it to use it for whatever we want. All right, so modular system. Again, we wanted to create a system that has a little bit more bite-sized chunks. We wanted to be able to separate the functionality, and we wanted kind of one group of related functions for each module rather than one blueprint to rule them all. So here's kind of how we went about structuring that. So we have a module controller, which is just a basic actor blueprint. The reason we wanted to go this route is because we wanted to just pull that actor just into any scene and it just work. So this allows us to do that. From there, we have a few different elements. We have a data actor component that is attached to that module controller. And that's basically going to control everything that relates to the data itself. It loads and saves the data, so from the manifest files and the scheme files, and it manipulates that data, things like that. From there, we have a 3D and manifest function, which again is an actor component attached to the module controller. This is basically going to manipulate anything within the 3D scene itself. It's going to change the manifest when a manifest needs to change, and it's going to change the scheme when it needs to change. And then we have a widget functions actor component, again attached to the module controller, which controls all the UI, the buttons, the menus, things like that. So this was just a way for us to kind of break it up and keep everything kind of separated from each other so that it would be a little bit easier to go in and manipulate as needed. Talk a little bit about our 3D scene. So we use world partition. I was a little hesitant to move over to it, but once I did, I was glad I did. It's really nice, actually. We don't necessarily use it to stream levels in the same way that maybe a game might do it, but we are able to set it up so that we have one level per aircraft, and that one level controls basically everything within the aircraft. We use data layers then to swap between floor plans and things like that. Allows us to manage everything within one level, and one of the nice benefits of this is we can have obviously one object that's on multiple data layers. This is just kind of a high-level overview of what our level hierarchy looks like. You can see on the left there we have kind of our main level. Then that's broken up into data layers, which are the layouts or the floor plans themselves. Then from there we break it out into a zone, which is an actor blueprint. And then in each zone are these child actor blueprints that we call monuments. And these would be like the seat or the table or the ledge. And then from there, we can have styling that we can add to certain monuments. So like the seat has stitching options, it has different options for the cushion, things like that. And then under that, we can change the materials as well. So just to kind of give you a breakout of what that might look like here. So this is our 600, and we have 4 major floor plans for this. We have like aft galley versions, we have 3.5 cabin options or 4 cabin options, and this is how we kind of can use the data layers to actually go through those floor plans. Under that, we have a zone. So if I actually go back here, a zone would be like this section right here. So you can see there's several zones along this cabin. Like in this case, there's 3 different zones. And within the zone, all a zone is basically just a scene component that we've added a few variables to its custom scene component. You can see the variables over on the side, and this is what the JSON files will store this information, and then the functionality in the backend will look for this to make it visible or invisible. And then each of these then are just child blueprints under the zone itself, and those are the different monuments that go with that zone. So here's a monument. This just inherits from a actor blueprint monument type, and it has these 2 actor components on it that will, this one will change the materials for the object. It'll automatically look for whatever materials it needs to and then change those based on button options. And then we have a style as well that controls the style. And then for the style itself, so this would be under like the seat monument. Again, we have just a scene component that we've customized with a few variables over here. The JSON files will look for these variables and then turn these particular options on and off. All right, so let's talk a little about our user interface. Again, we wanted this to be responsive, we wanted it to be scalable, and we wanted it to be data-driven. So I'm going to give you kind of an example of how we might spawn from a JSON file and create a series of buttons on the bottom. So here you can see we have kind of our main widget. We're just adding this to the viewport on start. It has a overlay here just to kind of contain everything, and then a scroll box down here at the bottom that's empty. And here we have a button widget. So this is a separate widget for our button. It's a little more complex, but all you really need to know about it is it has a header text, it has a background image, and then it has just kind of an invisible button over that we can use to like add tooltips and things like that. So this would be, again, it's a little more complex here, but this is how we might spawn a button based on a JSON file. So we have our JSON file up here. It's a little more complex than the last one. We have this object array called buttons, and then under that, each one of those objects has a name, a thumbnail, and a tooltip. And they're all slightly different from each other. And I'll go through what each of these does now. So first, we're going to load the JSON from the file. We're doing this just like we did before. We're using our VA-REST subsystem and then loading this JSON from the content directory called ui.json. From there, we're just going to get that object array field called buttons, and we're going to store that as a temporary variable in this function. Next, we're going to iterate through that JSON, those JSON objects. And for each one of those, we're going to create a widget of that button type. We're going to add that to another temporary array just so that we can manipulate that later. And then we're going to add that as a child to our scroll box button. So that's going to actually add this widget that we've created, and however many of the JSON objects we have, it's going to add that many to that scroll box. Next, we're iterating through those buttons. You don't have to do it this way, by the way. I just wanted to chunk it up into each section so you'd be able to see kind of individually what each one is doing. You can kind of have them go one after the other. But we're iterating through our widget buttons that we created. We're going to get the JSON button object associated to that. We're going to get that name, which is this here. So the first one is button 1, then button 2, then button 3. And then we're going to get the header text and just set the text to whatever that string is. Next, we have our, this is using our asset registry like we'd done earlier to actually get the thumbnail that's going to go in the background. So again, we're iterating through the buttons and then getting the JSON button associated with that. We're going to get the thumbnail, which is right here. And we're going to figure out which folder we're in and get that asset from the asset registry, from that object path. In this case, we're going to cast it to a texture 2D, and then we're going to set this thumbnail image from that widget button to whatever that texture 2D is. And then finally, we're going to set the tooltip text for the button. Again, it's the same basic process, but in this case, we're going to get the main button and set the tooltip text. So, this is a simple example, but this is basically how we created all the UI. It gets a little more complex for some of it, but this is basically how it worked. And then this is the result. So you can see that it's spawned to these 3 buttons down here. The text is different for each one. This is the background image. And then if I hovered over them, it's just an image. But if I hovered over them, you would get the tooltip text as well. All right, from there, let's talk a little bit about performance. So obviously, when dealing with Lumen and Nanite, it's done some amazing things, allowed us to do things we've never done before. But performance is certainly an issue that we need to tackle. One of the big things is you got to deal with performance and quality, and you've kind of got to figure out where that nice middle line is, between those. You're always going to be either GPU bound or CPU bound. In our case, we found ourselves to be both in different situations, so we had to do some performance enhancing on both ends of that. Here's just some basic console commands if you're not aware of them. These will help you to very generally see what the GPU and the CPU are doing, what the render thread is doing. So some of the issues we found on the GPU, Lumen is pretty expensive. It was about 1/3 of our rendered frame. Now, depending on what you're using this for, when you go to, for instance, the outside of the aircraft, it tends to not be quite as expensive as the inside of the aircraft. When you've got a long, narrow tube, that actually is, we've always had difficulty rendering that. It's always much more expensive than, certain other things you could render. You deal with a lot of Lumen artifacts, so a lot of it is, again, finding that balance between performance and quality. So you've got to, in our case, we've got to up the Lumen sampling and things like that to get the quality that we're looking for. But we've got to be very careful with our frames per second. And one of the things we had to do was limit our lights. So because we have a long, narrow tube and there's a lot of strip lighting in it, we had to find ways that we could kind of combine that lighting together, but still kind of get that ability to swap out different zones and things like that. But we tried to first add every single little light, and Lumen wasn't having it. We have not tried yet using megalights in it. That may solve a lot of that issue, but that'll probably be next on the agenda. So now, as far as the CPU is concerned, VA REST actually we found iterating through really large amounts of data and using VA REST to pull the JSON data, one thing after the next, sometimes had a performance hit. So we would have to sometimes store the variable locally within a function and then iterate through those variables instead of the actual VA REST JSON objects. And then loading levels, Nanite is obviously heavier than the way things used to be. So when we load the levels, we had to do some performance things. Because we're loading so many different variations of the interior, every one of those variations would load at the same time. So we had to change some things so where it would only load whenever you were using that particular element. And then obviously textures, because we have a huge amount of materials. Just to give you an idea, there's actually over 70,000 materials that you can put in our cabin. We have nowhere near that in this application, by the way. But we do have quite a few in this application, so loading all those textures can be expensive. And we used Unreal Insights Trace a lot in this just to trace down particular performance problems. And I'm going to kind of go into what that looks like, how you can utilize it for your own projects. So it's really easy to use. Down here at the bottom of your screen, you have a trace drop down, and then there's this little button right here as well. So if you click on the drop down, you can start a trace by clicking this, or you can just click this little button here. And basically what that does is it just, wherever you click that start trace, it starts tracing. It starts recording everything that's going on within the application. And then you can stop that once you've done whatever it was that you wanted to test. And then you'll get this huge amount of information like this. So please don't try to read all of this. That's a lot of info. You can see you get everything that essentially happens. So like this is a button click. So this is when I clicked a button. This is what happened. And you can see, this particular function happened, and then from that function this happened, from that this happened, from that this happened. And you can really get super granular in exactly what's happening. So like for instance, in this case, this function, this whole button click took a little less than half a second, which is not great. But you can see this function right here is like more than 3/4 of that. So we can kind of begin to narrow in and see, well, there's a lot of iterating going on right here. So what is that? Is there a way I could simplify that? Is there a way I could make it a little more performant? And again, we would have never seen that the VA REST was as expensive as it was without using Insights Trace, because that showed us, that's actually taking a while for those to iterate through. So here's some kind of basic lessons learned going through this process. Very hypocritical for putting this one on here. Please make better documentation and notes than I did. I have to now, after the fact, do this. But it's obviously, for anyone else who's going through your program, it can get really big really fast, and it's hard for people to find things, as I'm sure Brian can tell you. Not everything has to go in the JSON file. So I wanted to try to, I kind of had a knee-jerk reaction to say, okay, everything was hard-coded, now everything should be data-driven. But that's not necessarily correct. So Unreal makes these little sidecar files that you can create called data user asset files. You could put some of those variables within those files. And those you can attach then to basically any type of view asset that's in your project. So you could, for instance, have materials that are tied directly to thumbnails that are in the project, things like that. So, if I went back and did it again, I might try to use some of those techniques just so the JSON files themselves didn't get quite so bloated. Give everything a unique identifier. So some of our manifests started off not having a unique identifier. And by this, it's like, for instance, if you have 50 materials, each material has its own unique name. And the reason that that's important is because if you ever want to try to find that material in the application, if you don't put a unique name, then you're going to have to find some other way to figure out which one you're looking for. So just adding a unique identifier is an easy, quick way to be able to find those things in the JSON files. Some hard-coded is okay. Again, we tried to kind of go completely the opposite direction. We tried to put some functionality in the data-driven files that we probably didn't need to do. If you have specific functions that aren't going to change much, then it's okay to hard-code those things. Lock down the engine version. So working with our Viz team, we started in Unreal 5.3, and our Viz team started in 5.5. So when they gave us our materials, we had to upgrade to 5.5. There was no way around that. So lock down that across your different teams. Make sure you're all working on the different or on the same version. It's very important. We also saw a lot of CATIA to Nanite artifacts. We're still kind of trying to track down exactly what causes that, but you may see some of those issues as well. You can kind of fix some of those either by turning Nanite off for that particular object, which I wouldn't do a lot of because that can then affect performance a lot. But you can in certain situations, or you could go to an external DCC and try to fix some of those issues. And with that, I think we are done. So thank you very much. And I think we have a few minutes here for some Q&A. If anybody has any questions, you can come up to the mic right here.